So today we're going to be giving a brief OpenEEmeter 2.1 PR update. We're going to talk about the hourly methods just very, very briefly, as we've already gone over it twice now. And then most of this content is going to be about the current progress on the hourly methods that we're currently doing. So we are wrapping up OpenEEmeter 2.1, which is the daily model. And I'm happy to announce that everybody can go and install this right now. It is just a pip install EEmeter equal 4.0.0 alpha 2. And this is the most up-to-date version of the 2.1 daily model. Just a couple of little details about this. We have a quick start module in here that has a basic usage and implementation for the 2.1 daily data. This is to help you be able to adjust how you expect to use the model, as there are some structural changes to the input and output. Speaking of which, we have refactored the code and outputs and serialization, so you can kind of expect for some of these things to change. In the future, we will be releasing our comprehensive population level results. We actually need to run it on this most up-to-date version. This version is finished as of, I think, today. So pretty new, hot off the press. One caveat to this is that the current version does require Python 3.10. This is because in, I believe, the unit testing, or perhaps elsewhere as well, we're using match case, and we can fix all of that and just put in if statements. But we've realized that, oops, we were actually using a 3.10 feature in a 3.8, hopefully, version. So we're going to be patching that. So in the future, it will be compatible with 3.8 and above. Just another note is that this has been primarily tested with daily data. And so the billing methods and how the billing methods are going to be affected is as yet untested. However, we do have the legacy Caltrack 2.0 mode. So my suggestion would be, for the billing methods, probably just stick with the 2.0 for now. Now, on to the hourly model.
Guys, can we see if there's just any questions on that folks may have?
Thank you very much. Anyone have any questions?
I've got a question, but it's more related to the last thing you said than the actual updates, which is was there a time where we decided to dailifying the billing data was worth it? Do you remember any of that convo, Adam? I feel like years ago that was a thing, and that just came up recently, and so I wasn't sure if any of you guys remembered any of that.
Well, Steve, actually, I feel somewhat prepared to actually answer this question, only because I recently read the Caltrack documentation, the actual 2.0 documentation, head to tail, and the recommendation. Well, actually, maybe I'm wrong about this. You might know this better than me, Steve. Actually, I feel like what I read said that when you have billing data, you should peanut butter it out across the months.
Yeah, that's what I remember too. But I forget where that analysis was, where we decided that and why.
I have a slightly different recollection from recent jaunts through the API docs, that I think the EEmeter 2.0 already converts to the usage per day and normalizes by billing period length. So I think it does that already, Steve, if that's what you're describing, that it solves that problem automatically.
Yeah. Okay. Yeah. It was more whether there's still an option, I think, but maybe that's outdated, where you could just run it on the monthly data. I wasn't sure whether I would remember.
Steve, are you asking specifically about a distinction between billing data and monthly data?
No. Just billing and daily.
Just billing and daily. Yeah. So I can tell you, Steve, that within Recurve, we definitely do that, like peanut
the
buttering
butter.
of,
Yeah.
and I looked at the documentation, and I remember thinking, okay, we're doing exactly what the documentation suggests we should be doing by taking that step. And I think the reason it's important to take that step is, like, you can, if you have 30 days in a month that are all at an average temperature, you have actually 30 data points. And then the next month you have, maybe 29 data points. And the next month you have 31 data points.
Oh, it does a weighted average for you.
Yeah,
that's clever.
it helps with that kind of thing. And so you actually end up with like multiple data points that are being fed into the model. It's just that those data points are identical to one another.
But
Yeah.
I was actually going to, Adam, I was going to argue against it for the exact same reason that you should just feed in one row per month, because one, I think the methods already weight by number of days. So I think it solves that. And two, I think the adjusted CVRMSE is using the number of value, the number of rows that you're feeding into the model. And so you're sort of messing up the statistics, aren't you? If you artificially, create 30 times as many input values. Like, isn't it more accurate to say we've got 12 points in this model than we have 365 from a statistical perspective?
We also,
That makes
though,
sense.
have a limitation in the data. For data sufficiency, we basically say that for there to even be a cooling degree day section or heating degree day section, there is a minimum requirement of number of points. And I want to say that is 6.
And I think some of this comes down to the use of cooling degree days in the model too. It's like, how many cooling degree days do you have, and not cooling degree months. I suppose you could reformulate things for like cooling degree months.
I just think it fixes that stuff. I thought it fixed that stuff for you inside the model, like fixed the units and like normalized everything to per day and stuff. But
okay, I didn't mean to derail the whole thing.
No, it's okay.
I'll give it I'll give it a little bit more look into trying out the different options on the EEmeter thing. I was just peanut buttering it too, because that's what I vaguely remembered. But then I was like, why? And I forgot.
Well, I mean, and this definitely predates me. I mean, this goes back all the way to CalTrack 1.0, I think. And I wasn't even involved in the conversations at this point. So I can take no credit nor any blame for CalTrack 1.0 style requirements. I mean, I think even if this is something we really feel is kind of important to revisit, then like everything's on the table still. And that's actually one of the things I wanted to mention here. I know that there's still an open conversation around delivered fuels, and I consider that like still, it's not like because we're releasing OpenEEmeter 2.1 that we have to close the door on that conversation. Like, these kinds of things are still very open, and we can incorporate them into 2.1.1 or 2.2. The numbering convention, I don't know, it doesn't even matter. I've got, we're in a base 12 system, so we've got a lot, of numbers that we can use. And so if we want to do that, or if we want to make it part of 3.0 or like whatever. So I would put this out there too. Like, if people feel like we would want to reformulate this and are willing to like put in the work to figure out what's the best way to do it, we're open to that. So anyway, I would definitely encourage people to install this thing, check it out, use it. I think it's fair to say if you run into bugs or confusion, like, please let us know, because we can update the documentation, or we can update, the code if there's a bug in there. So this is that point we've all kind of been waiting for, where we've wanted to encourage, people to test this out, to review it on their own. And then if there are issues you run into, we're all human beings writing code that's very unforgiving and can hide errors all the time. So let us know if you do run into anything.
Yep.
And
this
Ethan,
is a
who like really who really truly are going to dive into this, if it would be helpful for you, for us to sit down with you and walk through some of this, I'm sure we'd be happy to do that too.
Yeah, all I was going to say for the rest of the community is, like, the 2.0 model will take monthly data. I use it that way. So if you sort of got lost in the whole peanut buttering conversation, like maybe there's nuances about which one is best statistically, but it definitely works with monthly. It gives you reasonable answers. So anyway,
Yeah,
not the
thanks.
focus of today's.
Yeah, thanks.
I need to
Ethan.
actually test that. Because the legacy mode of 2.1 is not actually 2.0. I don't know if it will still take monthly data. That's yeah, to be tested.
So the idea then, Travis, if you genuinely have monthly data, that the safest bet still is to use 2.0.
Use 2.0 or use 2.0 legacy and peanut butter it would be my two suggestions. I think long term we'd be better off making a model specifically for monthly and billing, but it's really a question of, is there enough support or need for that? I don't know.
The primary, just in defense of that real quick, like gas data is essentially where we're largely running into monthly data that we still need to worry about.
Yeah. So if anybody else wants to jump in and start working on a monthly or billing method, that'd be of great interest. And let's go ahead and move on to the hourly model. So just a very brief background for those who weren't here during the intro. We've already gone over this twice, so it's going to be even briefer than the last time, which was a brief overview. So Caltrack 2.0, it is a time of week and temperature model. The variables going into it are the hour of the week and the temperature, and you get a graph similar to this, where you have the observed value on your y-axis, hour of the week, on the x-axis, and you get a unique prediction for Tuesday at 7 p.m., Wednesday at 7 p.m., Sunday at 3 a.m., for all of the months. The way that we do this is that we have to basically calculate the annual weekly load shape for all of the individual months. We fit to each month, where 50% of a given month's prediction is based off of the model for that month, and then 25% for the 2 months shouldering it. So basically, you get a unique Caltrack 2.0 model for every single month. All right, that's it. That's all we're talking about for the Caltrack 2.0. I'll go ahead and pass this to Armin to talk about our current progress on the hourly methods. And Armin, do you want to go ahead and share your screen?
Yeah. Let me see if I can do that more efficiently. Okay. Okay, I'm gonna do this. Okay, can you see the screen?
You're good.
Okay. So, quick recap on what we talked about in the previous meeting. Sorry. Recap from here, yeah. So the current issues with the Caltrack or OpenEEmeter 2.0, we think it's a little bit overfit. I read the documents for the 2.0. There are some tests for making some beanings and number of beans and all of those things in a way that we don't have an overfit model, but still we think the model is a little bit overfit because you use all of the baseline data and fit the model on top of that. But still we're analyzing how much is overfit the 2.0. And we know that the model is pretty much incomplete for the solar PV customers because the error is pretty much double in the population level. And we can see for those days, we showed that before, that for those days that we have, for example, a cloudy day compared to the previous year, we can see the error is very high. So that brings up the opportunity for us to use the solar data to compensate that error. And we don't have a flexible input for the 2.0. As Travis mentioned, we have temperature and we have day of the week. I mean, time of the week. So we can't add, for example, solar or anything else. So we have two possible broad options to tackle this problem. One is to just focus on the AMI prediction. We have the weather data, solar data, and we can introduce categorical data and just focus on predicting what would be the next year or the reporting year model or counterfactual. Or we can go to the route with solar disaggregation, actually disaggregate solar from AMI data, and then therefore we have a solar curve and then a load curve, and then treat the load curve in a way that we treated with the other non-solar customers. And this is a little bit complex. It needs more sophisticated models. So we want to stick to the first methodology. And if we have time and possibility to tackle solar disaggregation, we would do it. Another thing we mentioned in the previous meeting, and there was different type of options for input for the current model or the new model that we want to explore. One of them is different types of weather data like temperature, humidity, wind speed, and all those sort of weather data. And the most important input, in my opinion, is the solar irradiance specifically for the solar customers, which is global horizontal irradiance. Again, if you don't know what it is, we mentioned that in the previous meeting. It's basically all of the irradiance that you can get from in any given location in a flat surface. And we can introduce contextual data, for example, day of the week and month of the year. So far, I'm using these counterfactuals. Contextual data instead of time of the week, because inside of each sample that we introduce to the model right now, we have a time series, and the time series is a day worth of data. That day worth of data, it depends on the input data that you introduce. If it's just a temperature, so there's 24 hours of temperature, this is the input, and the output would be 24 hours of AMI data. But if you want to add more input data like solar, we just expand this time. So 24 plus 24, that would be your input, and the output would be the same 24 hours AMI prediction. And right now we're using cross-validation methodology in a way that we have just the baseline. How we use a 24 hours window, as I said, as our sampling window. And we use weather data and solar data and contextual features I introduced in the previous one. And we do this strat, for example, which means in the test train, the portion of weekdays to weekends are the same, or the portion of the months are the same. So we just don't want that, for example, in the test set, we just have the January data, or in the test set, we just have weekend data. And the portion of these two, or in these couple of classes, pretty much are the same. So far, is there any question? Waiting.
A quick question. The assumption here that the initial thing we're talking about is year-long energy efficiency models, right?
Yes. Okay. For the demand response, if you want to ask that one, and for the demand response, I think we can use the AMI data or energy consumption data as another input, like for example, the previous day or previous week worth of data, and then predict it for the next one. So it had the option to do that.
So the upshot here, Armin, just to summarize, is we have 365 days of effectively baseline period data. So when we're using these models in practice, most often in order to make a savings measurement, right, we have a baseline period that is 365 days, and then we have a reporting period that is after the program implementation. And in that post-program implementation period, we call that, like I said, the reporting period. We're projecting the model forward, but now as a counterfactual. And one common way of testing the reliability, the predictive capacity of a model is to look at that counterfactual versus the observed data in that post-baseline period. But that what we are doing right now, as of right now, what we are doing is to say, look, there could very well be trends that are happening over the course of time in energy consumption data that would make a baseline period measurement and the subsequent counterfactual not as relevant to the reporting period data as it could be. So in other words, if there is a trend, like people are, maybe we're looking at a window of like 2022 and into 2023. And in 2022, there was very high inflation, and maybe inflation had an impact on energy consumption. And that took place in a way that was like a time series trend. Then if we get into 2023, if that trend is continuing or if it's changing, then we're going to be judging our model against observed data that's being affected in a different way by a variable that our model was not built on. So it gives us kind of a skewed understanding of how our model is performing. So instead of doing that, we are doing a cross-validation approach where all of the data that the model is being trained on occurs from that 365-day baseline window, but we're withholding samples of data as test samples from within that same time period. And then we're gauging the model's ability to form a valid prediction on that test data that we're withholding from within the same time period. I think this is a key point. And as Armin gets into it, we're going to talk about different strategies on how to approach this and what's leading us there. But I think it's a very important point. So I just wanted to emphasize what was happening there.
Yeah, thank you, Adam. 100% is that this is the case. And I just wanted to mention and emphasize that each day in each fold, we have, for example, we have 10 fold train test data set. In each segment of data, for example, train, for example, if the 1st of July is in train, we're not going to see that in the test. So it's totally separate as well. So those test data hadn't been seen when we are training the model. But I'll mention it in I think the last slide or a couple of slides from here. We're mentioning that we might try, we want to try another different type of test train split data set, and then K-fold, which is based on a year rolling window, and that rolling window is per month shift. But we need another almost 3 years of data to actually do the analysis. So that's for the future work. Okay. If there's no question, I'll go to recap for the preliminary result that we got. So in the previous meeting, I just focused on one model and tried to use the inputs, test train, and K-fold and all of those things to actually see if most importantly, solar data can help us to have a better counterfactual for the solar data as solar customers. As you can see here, in the first row figure, we have 2 days of data. I just brought random 2 days. And we just use temperature. So as you can see, the elasticnet, which is the green curve, and the 2.0 is actually doing a bad job for predicting or spitting out like counterfactual specific for the first day. It's doing a good job for the second day, and that's the reason is that we have more GHI or solar data in the second day, not in the first day. Perhaps the first day was a cloudy day and we didn't have that cloudy day in the baseline. But as you can see, if we use GHI, which is the solar data, which considered the cloud coverage and all of those things inside of that time series, we can see that ElasticNet used that GHI and have a way better counterfactual compared to the other one. Yeah, I think there's a question here. Yeah, Stefan.
Yeah. I thought GHI was like global irradiance data. Like it's not based on cloud, like cloud covers its own variable. Like isn't GHI
Okay.
just coming from like a math equation of like where the sun is?
No.
Or is it
So
actually
it's based on location. So
okay,
basically,
so
this
got
is
it. So it's sorry, I missed the last thing. So yeah, it's the GHI's post cloud cover actual measured weather station data.
Yeah.
Okay.
That
cool.
GHI, that is just, you can calculate it based on the equation. That's a clear sky GHI, and it's dependent on the time of day and all those things. This one is actually the GHI data with the cloud coverage that this meter that matched to that weather station. So this is the data for that weather station that we pulled and measured to the actual data.
Cool, thanks.
Yeah. So, and that was the recap. So there was a couple of future steps that we mentioned in the previous presentation. One of them was that we wanted to explore multiple models, a couple of models and different inputs. We decided to use two distinguished models. One of them is ElasticNet, which is pretty much cover linear regression, lasso regression, ridge regression, and all together. And we change the parameters within, like for the L1, L2 norm, in different ways, in different basically scenarios, so we can explore that area of the model. And then we use an ensemble model, which is extra tree regressor. It's pretty fast. It comes from the random forest family models, and this is pretty much representative of those type of models. So these two models are being chosen to just test and analyze how they perform. And we use different inputs. For example, we have just temperature only, temperature and GHI. We have a couple of weather data like humidity, wind speed, temperature all together, with and without solar data. So we have many scenarios that we analyze on different type of data sets. One solar customers and the other one is non-solar customers. And inside of each population analysis, we have around 1,000 meters. And at the end of that, we evaluated the models based on CVRMSE, and one thing that we introduced, PNRMSE, which is percentile normalized RMSE, which I'll explain the next slide. And we took a look at the calculation time for these models. So what was the CVR RMSE? Is the coefficient of variation of RMSE, or root mean square. Basically, we calculate the RMSE for each period of time that we wanted and divide it by mean value of the target variable, which is, in this case, is Y, or in our case, it's AMI data. And there's a problem with this, which I'll show you in a couple of next slides. When we have solar data, this mean value actually is either so close to zero or negative. And most of the solar data, actually, the size of the solar panel is being designed to meet the demand of that house. So that makes sense if the AMI data is almost zero or negative in many cases. That I'll show that later. And there's other type of criteria that we can consider is relative normalized RMSE, which is, instead of dividing by mean, we're dividing by a range, which is max and mean. And we know that in the time series data for a year or more than a year, definitely we have some anomalies, and the maximum and minimum are not prone to that. So that range can actually be very high, and that when it's very high, the RMSE divided by a big number is close to 0. This can be misleading as well. So there's another one that we're using, and we think maybe that's a good option to replace it with a CV RMSE, is a percentile normalized RMSE, which is pretty much the RN RMSE, but instead of max and mean, we have 95 percentile and 5 percentile AMI. This range is more reliable in a sense, and then divide RMSE by that range. Okay, before I go to the next slide, is there any question? Yeah. Glenn?
Sorry about that. Yeah. Super sorry. Can you repeat what the problem was with the CVRMSC? What kinds of scenarios where it's kind of troublesome and why that is?
Yeah. So, for example, we have the solar customer, and we know that at night we have positive, and then in the middle of the day it goes to the negative, and then comes to the positive. But the net value of that, and I'm sampling for 1 day, that can be expanded for a year. For that 1 day, the mean value of the AMI can be either 0 or maybe negative. So,
I see. I see.
yeah, that CVRMSE can go to very high number or negative, which I'll show you in a couple of next slides.
Right.
I'll
So-
bring a histogram.
I got it. That makes sense now. I forgot we were switching to the average daily usage, and so that takes out some of the variance associated with using a parameter to estimate a parameter, an average to estimate the parameter of that average. But anyway, I'm not sure that makes sense, but I get it now. Thank you.
Yeah, sure. So let's go to the next slide, which are the population results of different scenarios that I mentioned. I just brought a summary of that in these slides, but I wanted to actually walk you through to this figure. We have 3 histograms. The first one on the left always is for the OpenEEmeter 2.0 or the Caltrack 2.0. So basically, that's a histogram of the CVRMSE for the 2.0 on the left side in the non-solar residential population that we analyzed. And the input data, as you can see, it's a temperature and the GHI. The model we use to train this specific scenario is extra-tree regressor model. And the 2 right figures, we have the new model errors. But the first one, we're in the middle figure here, we have the histogram of the error or the CVRMSE for the train set, and for the right side, we have for the test set. As we can see, for the train set, we have almost 61% improvement compared to the 2.0 and 33% in the test set improvement compared to the 2.0. There's a huge difference between these percentage improvements, and that's because of extra-tree regressor or those random forest methodologies tend to overfit. Even the parameters or depth of it is like 1 or 2. Still, they can have a very, very low train error, and the test error is good enough, but there's a problem that we can see. It's pretty much overfit on the train set, and this is something that we need to consider for the future analysis.
Before you go on,
So if you do the, sorry, go ahead.
one thing to note about all of these plots is that when we're showing OEEM 2.0, you can basically treat this as the Caltrack 2.0 training data set, because we don't have an analogous way with this way of doing cross-validation to calculate what the test data set would be.
Yeah, that's a good point, actually. So basically,
Which
when I
means
say
that the error metric is a lower bound, effectively. Like the error
the
metric,
test
what is
data
the,
set.
the CVRMSE is what, 0.12, the median CVRMSE? 0.12, am I reading that right?
Yeah, yeah.
So 0.12 is the median error metric. That should be considered a lower bound.
Yeah. And then we can see the improvement in the test data set. So that test data set error is the most important thing for us because we're using the cross-validation, and this is the more realistic expectation of the future error. That is the mean value of the tested error. So this is basically structure of these histograms. And in the next slide, I just chopped them up, and the left side we have again the same thing. Everything is the same except the middle histogram. The left side still we have the OEEM 2.0, and in the middle is the same extra tree regressor model that we trained on the temperature and GHI. And the right one is the model that we trained based on not all of the most relevant weather data that we had, like temperature, wind speed, humidity, and so on, and the GHI. So, and these the two figures on the right side, there are the error for the test data set for these two scenarios. And as we can see, even just by using temperature and GHI, we get a better result in terms of error improvement. We have 33% improvement when we just use temperature and GHI, and the other one is 32% improvement. They're pretty close, but when I check all of the scenarios that we had this with different models or different parameters, this was the case. So that means adding more weather data, at least in these scenarios and these random data set that we have, they didn't help. So sticking to the temperature and GHI maybe it's a good idea. And for this type of methodology, well, the type of model, extra tree regressor, the calculation time with the VM that I had is almost 2 minutes for 1,000 meters. I can compare it to the next slide. Okay, so just the calculation time. Now we change the model right now. Instead of extra tree regressor, we're using ElasticNet. The calculation time went from 2 minutes to 9 minutes. That one was better in terms of calculation, but as you can see here, we have the 2.0 on the left, train in the middle, test on the right side. As you can see, the percent improvement or the median PNR MSE for both of these train and test are pretty much the same, or they're so close. That means that ElasticNet is just right model, or it's not overfit. At least it's not overfit in the train set. So this is more reliable in terms of reporting the error for the test set. And this is for the solar residentials. And this is pretty much the same for the non-solar data. ElasticNet is more robust in terms of error for the train and test, and it's not overfit. So I just want to have a quick pause here, and if there's any question.
I've just got a.
I'm sorry, go ahead.
Oh,
Stefan.
sorry. Okay, yeah, I was just gonna ask if there's any. This is maybe a bigger question, but moving from like the regular regression to these more complex models, if if there's any concerns on like interpretability, or if it still feels like there's like ways that we're able to interpret like why something predicted the way it did with these new models because of how they're structured, and also, or maybe like if you found like that's less of like a concern, that people accuracy sort of is more important than kind of that interpretability like balance.
I don't know, Travis, do you want to?
Yeah.
can answer
So
that.
right now we're basically looking at this like, yes, technically, if you wanted to go into Caltrack 2.0, you could look up all the coefficients, but there's so many coefficients, it's basically a neural net by itself. Is there really any difference? And is anyone actually going to go in there and look at those things versus just fit the model and get a prediction? And like, I know that us at Recurve, we don't ever go into it. We use it purely from the perspective of we want to predict whatever the model is doing. So we're we're basically saying, let's just drop the facade that it is in any way being able to interrogate it, I guess. So drop that, get a better accuracy. In the end, I think it's beneficial for the model and for us all.
Travis, so very different perspective here. We're still talking about the daily, right? We only
No.
have, oh, we're
No.
back down into the hourly again. Okay.
Yeah, it's all
All right.
hourly.
Okay. Hourly coefficients, we've never known what to do with. I can roll.
Yeah, that's kind of the thing is the hourly code, like the daily, when we got into the daily model in the 2.1 phase of this working group, we felt like we really needed to retain the ability to produce heating and cooling disaggregation. So we structured the model just from day one with the boundary condition effectively that you had to be able to do that. So it's a 2.0 style model. It's just split in ways that avoid seasonal bias and all that kind of stuff, as we've talked about a million times. In the hourly model, we, like you're saying, Ethan, like we don't really know what to do with the coefficients anyway. But I also would say I'm not an expert I'm not as much I'm not as knowledgeable as Travis and Armin are about some of these machine learning methods. But with an elastic net regression model, you have parameters that effectively downweight some of the coefficients, and that downweighting is guided by a mathematical parameter that you can access. So it's not as though it is I think where we cross that Rubicon into and we actually, if anybody remembers the very first working group meeting that was focused on the hourly model, we were asking ourselves, do we want to go into a deep learning neural network type of approach versus a supervised machine learning model type of approach? And a linear regression, just straight up, is a supervised machine learning approach, just in and of itself. This is just a variation of that where coefficients are downweighted according to another parameter, but it shouldn't be thought of necessarily as inherently less interpretable because of that.
Yeah, sorry, I missed that sort of key factor. And I would say, like, we haven't even done the bare minimum with the existing 2.0 hourly, which is to constrain the model to not have, negative slopes where it's physically meaningless. So if we can't even do that, then what are we holding on to? So yeah.
Yeah.
And to be honest, in the elastic net, we have less parameters in general compared to the 2.0 with the baseline that we have already. And basically, elastic is linear regression plus a penalization factor, and that is just penalize the whole the coefficients on the left side, which is pretty much this, in my opinion, simplest model that we can actually use. Introduce time series to that based on the input definition that we have. Travis.
So first of all, to re-clarify, in the hourly model, we don't care about what the coefficients are because there's so many of them, it's nonsensical to even say that we know what's going on. In the daily model, it was a big concern for us that we maintain interpretability and be able to disaggregate and all of that. So I guess I would just ask a broader question to everybody, and that is there any opposition to what I'm saying right now? Like, does anyone actually want to keep the, I'm going to use air quotes, but interpretability of the hourly model? Like, what if we did go to a neural net?
I would say that, what you've explained, that elastic net probably is no more complicated than the hourly regression one. But I would oppose the neural net sort of jump just because, first off, data requirements and those other sort of things, but yeah, I recently, I'll have to share a notebook out once I clean it up a little bit more, where we were trying to do some interpretability around the hourly coefficients, specifically for demand response. And just in the case of like being able to build out that, U curve that based on the different temperature bins and things like that. And you know, honestly, I don't know. I mean, I was able to make some plots that gave some meaning. I don't know how actually interpretable they are. But that sense of allowing someone to be able to understand how we made a prediction through like going through the steps, I think that's the part that I would want to hold on to. So I think in Elastic Net, if it in the approach you're saying sounds similar in that you could explain how these coefficients came about, you know, that how this took place, and then this prediction is based on this model, and you know, if you're able to still kind of describe the step-by-step process and have the steps be somewhat interpretable, that's still important to me.
I mean, I'll say for the daily, I'm strongly attached to the coefficients. I built a whole diagnostic dashboard that makes use of the balance points and slopes to try to help people figure out what the right solutions are for projects that are underperforming, things like that. So as much as I know that there are times where it might be misleading, I think there's enough value in there that it's definitely worth hanging on to. So I'm glad we've kept it there. I'm not, I think for cases where we have hourly data, just downsample it to the daily, use that, get your answers out of it, or maybe, you know, we can find some other ways of interrogating the models, is my personal feeling. I'll sort of defer to others about what the right level of complexity is to go with the models and like where they can start to send us wrong and we won't know the difference. I mean, I'm not sure we're going to be doing like test and train on all of these data sets, right? We're using these to calibrate the, you know, meta parameters, right? The hyperparameters, and then we sort of let it go, and then at that point we like dive into the abyss and hope that everything still works right with our particular data set, you know, and then you wonder, oh, we're doing multifamily in some weird climate that was never done before, and like, how do you sort of take a look in your model and go like, yeah, that doesn't make any sense at all. Why do we have a, you know, 30-degree balance point on these homes? That's crazy, or whatever, right? Like without that, so that's the piece I think that we just need to figure out, like how are we going to continue to sanity check these as we sort of move into new spaces, right? We sometimes use these, like, so I've used these models for things like, oh, let's take runtime off a furnace and then multiply it by, you know, the capacity, and like, why shouldn't it work? It should be fine. But you kind of want to check and make sure, right? So as we get into some of these things, like we won't necessarily know where the edges are. So it's just something to think about. The power of the tool, just plug it in, it goes, it's great. And that's the risk. So that's all.
Yeah, like for example, the one thing I found with like some of the DR stuff was like, oh, I can tell why this prediction, this seems to be under predicting significantly, this because I can tell that there's temperature values out like in the reporting period that are outside the baseline, right? And maybe that's not even something, that's something you'd be able to figure out without interpreting the models themselves. But there's sort of like that sort of stuff that Ethan's talking about of like how to tell when it's less when the things are savings are good. It's more like when something is weird, how able you are to sort of figure out why it's weird, right? And I think that's where like, you know, that like that Rubicon Adam's talking about, right? Like still being able to sort of diagnose or like figure out what's going on in a specific case is always going to be helpful.
So specifically for the demand response, because I worked a little bit on that before a couple of years ago, and the best predictor for the future or the next day AMI data would be previous days, not even temperature, not even anything else. Those pattern of usage, specifically a week worth of data time series, would be a higher predictor in terms of ranking. And then when you add temperature to that, and then a little bit improves. When you add GHI to that, those important ones, specifically if you have a solar customer. So if that's the case, if we want to introduce input features like historical AMI data rather than those type of data set like temperature or GHI, I don't think there is any way or any model that we can interpret anything based on those inputs, unless we just wanted to stick to the temperature and the binning the temperature. Anything rather than that, any coefficient would act differently based on each meter data, because each meter data is different, and each meter data is different has a different connection to the previous data that it has. Personally, I think that's a second priority for the hourly model, because the most important use case for OEM would be MMV. And MMV in terms of how we can have a pretty good counterfactual. And if there's any like data analytics on top of that that we can build, that would be the secondary goal. And this is my point of view. I'm just like putting it out there.
Yeah, I think Oh, go for it, Travis.
I definitely concur with Armin in that if you just think about this in terms of like experimentally, the more coefficients that we're adding, the more that these coefficients can also act against each other and change each other, which makes the interpretability even harder. So like if we want to be able to add in GHI and possibly any other time series that the customer, or not customer, that the NV users want to add in, it's going to be more and more and more difficult to understand how these correlate with one another and how they affect each other. So that's why I think that the more complex we get, the less that this idea of interpretability kind of can even be feasible.
Yeah, and I think there's a difference to be made between interpretability in the sense that there's a physical interpretation of exactly what's happening in the model versus interpretability in the sense that there's a mathematical explanation that is readily accessible. And so if we switch over to like a neural net, for example, Armin likes to point out to me that, hey, it's all math, right? But there's a very complex set of optimizations that happen in a neural net, and there's backpropagation and like all of these kinds of cycles that you go through, these epochs and optimization, like all that kind of stuff that happens. And yes, there is a math, it's all math, right? At the end of the day, it's all math. Nobody's waving a magic wand in a neural network. At the same time, when you have something like an elastic net, even if it has many parameters, then even in a multiple linear regression, just forget about an elastic net, just take a straight up multiple linear regression. You may end up with certain parameters being like highly negative that they in their own right are correlated with positive energy consumption. And so it's like, why is that coefficient negative? You lose a degree of physical interpretability. It's the interaction of all of the parameters together that matters in the end. So I think we should, when we're asking ourselves like what's really important, I'm just kind of making the point, there is a distinction to be drawn between the physical interpretability of like any individual parameter, which is something that we've tried to really maintain in the daily model, versus a mathematical ability to interpret something where you don't have to be like literally going into a neural net and figuring out every element of the backpropagation or of the ReLU network or like whatever it is. So anyway, I'll get off my high horse here. Glenn, I see you have a question as well, or thought.
Yeah, just to change the subject. Sorry, we can continue on if you like on that one too. But just real quick, in some of the previous histograms we were looking at, I was just kind of visually inspecting them and seeing where these big percent changes were coming from. And it looked like the tail end of the distribution is where all the kind of the improvements were happening. But when we got to the later histograms, it looked like maybe all the improvement was coming from, the high end, right? And it was an observation, but then it occurred to me, well, do we really care if we're improving on that 340 2.0? If we're not going to use those anyway, right? So anyway, just kind of an observation and a comment.
Yeah.
Does that make sense?
Yeah. So we can do a couple of things. There's only one benchmark that we have, and that's 2.0 output or counterfactual for each year for each meter. So naturally, we wanted to compare that first with the 2.0. There are other models out there that we might approach and actually model them, bring it, use it as a benchmark, evaluate based on that. We can even, not we can, we will have a neural net model. We will have a more complex neural net model or different type of models, and we compare them based on different parameters like calculation time, how many parameters they have, or what is a tester or trainer, are they overfit or not. So there are a bunch of scenarios and models that we can consider, and one of them I think and it's like more natural to do is comparing to the 2.0.
Right. I was just making a comment that a CBRMSC, a histogram, that big spike on the left-hand side.
Yeah, and
We
Glenn,
don't
actually,
we don't really care about those, right? Because,
well, maybe not. I mean, I would argue that, you know, if you look at the median values here, I think Armin, I think Glenn's raising a good point in the sense that it would be nice to see. It's nice to see these histograms with the big long tail. It might also be nice to see these histograms, you know, cut off at like 0.4 or something like that in the binning MapeFinder around there, because that would give us more direct insight into what's happening with the bulk of the meters. But I would point out, if you go back to the previous slide, Armin, like the one you were just on with the solar, which one? It was the, yeah, the OpenEEmeter 2.0 model has a median of 0.95. Is that, am I reading that?
Yeah.
0.95. And the median in the Elastic Net on the Crane data set, or on the test data set, sorry, is 0.52. So that median of 0.95, like I said earlier, should be really considered a lower bound, where that's a significant improvement.
Yeah, for sure.
In the median value. So like we're definitely seeing that it's not just a few meters or a few customers or whatever.
Sure,
that,
sure.
you know, it's
I'm not saying it's changing the story or anything. It's just more of an observation, and maybe it might be a little more accurate.
You're absolutely right. It's a very good. It's a very good point.
Actually, I wanted to plot with all of the tails, and I did for the CVRMC in the Nexus slide. Those anomalies are huge, and I was like, so nobody can see anything, let me just cut it off like 5% to actually we can see what is the median and what is the slight difference that you can see in the median on the 2.0 and the other new model.
Right. Or overlay each one with a different color. You can see which part of the bars are where we're getting the big savings from or something.
Yeah.
Anyway, just comment. Thank you for listening.
Yeah, thank you so much for
thank you for bringing it up.
Yeah. So let's just move on to the next slide real quick. I need to run here. What is that? Where were we? Okay, so we had ElasticNet here, train set, test set, the new model. We have pretty significant improvement here, and we can see it's a little bit slower, but it's not overtrained. That's a good and bad part about ElasticNet, and it's pretty much simpler. So this is actually the CVRMSE versus PNRMSE for the solar residential for one of the scenarios that we had. And actually we're using ElasticNet model here. So as you can see, CVRMSE in the left side for the 2.0 and pretty much for the new model, because of that range that we introduced for the solar model, some of them, the average is negative. So the error would be negative. So there's we can't even compare them with the actual error because we know RMSE is positive. So that's one of the downside of the RMSE that we need to consider. And sometimes, even if it's not zero, even if it's a negative, it can be so close to zero because we have solar data, solar customers. So the average can be zero. And then the error would be misleading because we are using an error divided by basically zeros, and we have a huge number for it. Let's move on to the next one. Okay, so this one, I wanted to show the impact of using GHI on the solar customers. Travis brought it up today. it's not as exciting as we want it to be. So that can be because of a couple of reasons, which I'll mention later. So basically what we can see here, these are for test data set, and we are using ElasticNet, same parameters in terms of penalization and all those things. In the left one, we're just using temperature. By just using temperature and the new model and the input data we're setting up, we have a 41% improvement in terms of, I think this one is PNR MSE, compared to the 2.0. But if we add GHI to the temperature and do the same thing and train the model ElasticNet for the same population, we get 45% improvement. So that 4% improvement, it doesn't look much because we already had an improvement based on the setup and the methodology that we have. It's either we have very low cloudy days in the population level because we're using California data, or there's fundamentally something wrong with the training test split that we do. One of them can be solved with those rolling year window that Travis suggested before, which we will do that later on. And yeah, this is something that we need to consider and take a look at it. Maybe that GHI, it'll improve 100%, but
yeah, well, Armin, I'm not surprised by this at all, and I wouldn't dismiss a 4% improvement. I think what matters is de-risking the model for what you talked about a few meetings ago. You know, a few meetings ago, you talked about what would happen if you only have temperature data, and in January of the baseline year, it's sunny, and in January of the reporting year, it's cloudy. That's the problem we have to solve.
Yeah.
And I wouldn't be surprised. I mean, we're talking about data in California. It's the sunshine state. Literally, that's its nickname. I would not be all that surprised. I mean, I lived in California for 10 years. It rained like 3 days. So I would not be surprised at all if this is a reflection of having relatively few cloudy days and you're seeing an improvement nonetheless.
yeah.
But I think it would be very smart for us to isolate the days that in the test data set that are very cloudy, that have low GHI. And
Yeah.
let's see how the model behaves on those days.
Yeah. Two things real quick I want to add here. One is that I'll get back to you, Steve. One is that this GHI didn't change, didn't improve the error for those non-solar customers that much. The test error, the CVRMSC for the cross validation of test error for all of those scenarios that we consider for the non-solar customers, pretty much the same when we are using GHI. It's not that different. But for all of those solar scenarios that we consider solar and not consider solar data for the solar population, all of them that we have solar, we have improvement, at least for 5 or some of them with 10% improvement. So this is specific one is like 4 or 5. Steve.
Yeah, this again might be something that I missed at that first meeting you were talking about this, but kind of like what Adam was saying, it like and something we even found from like the existing hourly methods is the hour of week is pretty good at capturing solar generation. It really is just the cloud cover like that. That's the real piece of information that is missing from sort of like, or like the difference in cloud cover is really like the real piece of information that you're missing. And so is cloud cover like I guess maybe GHG is more directly like shows you the impact of cloud cover on the sun, but I wasn't sure whether like percent cloud cover or like if there's any reason to not like kind of double use that.
So basically this GHI is that clear sky GHI multiplied by cloud coverage. That's pretty much it. But it depends on the DNI and DHI and the source of data that we are using. For this specific example, we are using NREL data set. And for the other ones like Soulcast, Solar Anywhere, all of those, they have a pretty basic model or formula that you input DNI, DHI, and cloud coverage, and they give you the GHI that you have, which we are using it like as a column here.
Yeah. I would just wonder if maybe that like there's some, it might be not a big deal, but like whether there's some overfitting of like if you have the hour of week parameter or some sort of like hour of day parameter that already kind of factors in that natural sun, and then like you might not need even like the global clear sky irradiance. You might just
Oh.
need cloud cover as like a variable.
I think there's a okay, we can calculate it. So, but you need to have DNI and DHI because when you have cloud coverage, DNI is the lowest part. So DNI is the direct normal irradiance. You actually need to have it. And when you have more cloud coverage, then DHI goes up because you have more reflection from other objects around you. So that's something that actually need to be measured by a sensor or something, which those data set that they have. And that's why we're using the product of that, which is GHI. So it's not like, honestly, I think if you have just the cloud coverage, that actually can help too. I mean, temperature and the cloud coverage, I think that can improve your base error. But if you have GHI, I think you have a higher chance to get a better result.
That makes sense. Yeah. I just wonder, like, I'm also on non-solar, I imagine cloud cover and those things might also have some effect on this, which also is why you might be seeing improvements with GHI, even on non-solar.
For the non-solar, we didn't see that much improvement. Maybe 0.01%, 0.5%, which is not much in the population, but it's still a little bit. But the difference in the solar customers versus non-solar is significant.
One thing that I just did a quick calculator on it is that it's actually a 10% improvement using the GHI. Like if temperature was our baseline, it's a 10% improvement to add GHI. So,
and this is just 4% here. As you remember, Travis, like a couple hours ago, I showed you the one of them was like 33, the other one was like 40 something. So it's like more 10%, 8%. It depends on the scenario and the data set that you have. Okay, let me move on to okay, this is one of the data sets that I'm dealing with. The EVO data set, I don't know if you heard about it. This is like a test data set for MMV. You can actually put your model, upload, get the data, use your model, train on the train set, and they have a test data set that's just the temperature. And you have your counterfactual, merge that table, pass it to them, and they'll evaluate it and give you, basically put you on the map here, wherever you perform. I found CalTech 2.0 here somewhere on 36. I should have put a bigger picture here. 36% severe RMSE as a percentage here. And there are a couple of other methodologies are better, but we are trying to, as we develop our model with our own data set, we try to test it with these EVO data set as well, which I don't like this data set. Okay, so this is the framework that Travis suggested. We needed more data. So basically, we train on the first year, evaluate on the next year. But within each train year, we don't use all of the train year as a huge time series and then train it, and we have 1 year as a huge time series. So basically, within the train set, within the train period, each day, each like 24-hour window is still the same. That subsample all of those, which means within a year we have 365 samples, and we train based on those. But the actual train period is changing, so we are shifting the whole thing 1 month, and the next time, which is another pretty much k-fold for us, we train on the next year, and we train on the training period, which we shifted 1 month, and then test it and evaluate on the year that we shift that one month, and all the way to 12 months of shift. So basically, if you want to look at it, we need 3 years of data for those meters to evaluate on them. So in the future, so we need 3 years of data for these meters that we want to develop the model and optimize the hyperparameters for it. So in the future, we don't need that 3 years of data to train the model. Basically, here, this is just for R&D purposes. We hope that this can give us a more realistic test error of each model that we train, and compared to the test train that we already have. We have a year, stratify sampling, test train. And this is a little bit more like shifting towards the future and pretty much see the trend of the future that happens.
So the primary advantage to doing it this way is that it will replicate exactly how the model is used. And the reason why we are doing these 1 shifts in 1 month shifts is because there's always the possibility that we can have some crazy data or some crazy event happening in the train period or in the test period. But if we're constantly rolling this window, then that's all going to basically, at one point it's going to be in the test period, or could be in the test period, and then in another it'll be in the train period, and it's all going to basically smooth out to give us an estimation of what the true test error is. Now, the reason why this is likely a better solution than doing like a 90-10 sample as you're suggesting, Ethan, is because think about this in terms of you're being timed how long it takes you to drive from one location to the next. You know where location 1 is, you know where location 2 is. Even if you take out all of the information about velocity in the center, you still know what that average velocity was because you know the starting time at the beginning and the end time. So inherently, if you're pulling something out of the middle, you still have some information about that because we live in a continuous world. So this is trying to basically eliminate that problem while also allowing us to estimate what the true test error is. Side benefit of this is that this is also very easy for us to implement using Caltrack 2.0, just as we can do it with our current model. So we will also get a test error for Caltrack 2.0 that we can directly compare to our model's test error.
I guess I'm just sort of, and I know this is what we always do, right? This is the same thing that Evo test set does, right? Is it considers that if a particular meter wasn't enrolled in a utility project that was part of the data request, then it must have had nothing change in a 2-year period, and therefore we can look at the error between a prediction off of a model from year 1 and say that 0 is the right answer for a model. Having been in buildings, stuff is constantly changing, right? Like it's kind of ridiculous to take 0, and we also know that there's biases for different building types to increase or decrease over time based on codes and standards, whatever. I'm preaching to the choir, right? We've all seen this stuff. Like, this is the world we live in. So that's like, I hear what you're saying, Travis. I think about how that a model trained even with the the gaps has some understanding of what's going on there, but I mean, I guess as a relative comparison, but I don't know. You hear my sort of fundamental disquiet, and this is not about this particular exercise, because we do this all over the place, right? We take a bunch of random buildings and then we say, let's assume that nothing changes, and we go on from there because we got nothing better.
Mm-hmm.
Yeah, I think I think Ethan, the thing that's like triggering us on this a little bit is getting some results from the Evo thing itself that lead us to believe that maybe we have a blind spot somewhere in the cross-validation approach. And maybe it's maybe for reasons that we actually can't even articulate right now, we need to be looking at reporting periods. It is a little disconcerting that when we have a model that seems to be performing very, very well in the cross-validation test data sets, that it is performing somewhat poorly on the Evo data set. If I were a betting man, I would bet that the Evo data set itself might have some issues. But I don't think we should take that for granted. And this is a good way. I think we're talking about using this sort of in addition to the cross-validation approach, and being able to compare and contrast between the two of them. I will say, one thing I would ask the group, if anybody's ever thought about this, is like we always think about these models as like linear in time, in the sense that the baseline model has to be on the baseline period that happened in the past, and the reporting year model is on the reporting period that's happening in the future, like relative to an intervention active date. But that's not necessary, I think. I think what we need out of this kind of a approach is the proper staggering of things, so that we have equal representation of any given time period in the baseline period, as well as the reporting period. And I wonder about an approach where we actually turn the tables and we say, look, we're going to train the model on a future period, and we're going to test it on a like previous period, a time period in the past. There's no reason, like in a sampling like this, that we have to train a model on data that happened on 2021 and use it on 2022. Like, we could train it on 2022 and use it on 2021. And I wonder if that kind of a flipping, like doing that kind of staggering, where we're also building models on the future, testing them on the past, would allow for fundamentally just equivalent usage of every data point in a reporting period, and equivalently in a baseline period, just depending on the sample.
Yeah, I mean, I hear what you're saying in there, Adam, and that's, I mean, I think you sort of get twice as many answers out by doing it in reverse. It doesn't eliminate the issue that like something can happen in the middle there, but it sort of broadens your perspective on it. The one other suggestion that I would make is that the staggered approach that you're using looks very similar to me to an event detection algorithm that I implemented like way back in the day, where basically if you have an event and you're doing a comparison between two sliding windows and the event passes from one window to the other, and you look at the sort of like ratio, or this, in this case, it's going to be the error factor, and it like suddenly jumps, like that's kind of an indication that the error has just passed over your threshold between the two systems. So this might also let you sort of flag some of the data sets where you have a particularly strong signal in that way, where like suddenly the error jumps at one point, and that might cause you to like pull out some of those data sets and be like, this data set seems like it has an obvious difference somewhere in the middle. And so maybe it's not a representation of like model accuracy anymore. So let's downweight the error from that model.
That's actually a really
Before
good point. And go ahead, Travis. You wanted to talk?
Before I forget, Adam, I'd actually expand on that idea that you had. I think that we can do better. We can actually take January from the test period and put that in the train period and flip the Januaries. We can flip the Februaries. We can basically just do all of that, and we can make as many test sets as we want.
Yeah.
That's a good idea. Before I forget, also, Ethan, you asked earlier justification for this. This is actually kind of a typical data science approach to how to test train time series. It's a slight variation. Normally, you vary the train period and you also vary the test period. That's not as applicable to our situation as it is in a lot of other data science approaches, but that's basically where this idea came from. And the reason for all of that is basically to make sure that you are providing zero future information to the model. That's the most critical thing that you can do.
And one thing I wanted to add here, basically, of course, we can use it for event detection because it's rolling window, those like regime change and all of those things that we can see pattern changes. But because we're doing it, for example, 12 times, and we take the median error, therefore that will be a good representation of the future error. Although we might have some huge spikes in terms of errors or low spikes, but the median would be a good representative because the median is removing those anomalies, and we have a more realistic test error.
Yeah, I sorry, I'll pass it to you in just a moment. The current implementation, I think it's a perfectly valid way to do things. If we can get a data set that is, I say this very, very cavalierly, roughly unchanging, which even if it changes a little bit, it's okay because it'll all kind of smooth out and we'll get a average or median error, which is ultimately the goal. All right. Dr. Steve.
Steve.
Yeah, I just had a question around this. This sounds like it might help with this, which is like solar, people who install solar part of the way through the baseline or reporting period. Like, is that something that's this like is part of the data set? Or is that like way just like overly complicating everything? Is it like is the assumption here that somebody's had solar the entire time or not?
That's what makes this difficult because we really want to avoid anybody who has had a change in solar status during those 3-year time period.
Yeah, upshot, Steve, is at least at this point, like that's not a problem we're trying to solve right now.
That's what I figured. Just what was making sure.
Yeah, but it's totally a good point. I mean, it's like, what do you do with that? You know?
Yeah, I mean,
Caltrack,
you're already
yeah, OpenEEmeter 4.0.
Yeah, I mean, you're already like if solar is the project, you're fine, right? Because you're measuring the impact of solar itself, and then it's just then it's just like so now there's just you can either solar be the project or solar be something you've had for at least a year. It's basically the requirements, I imagine.
Well, I mean, Steve, I can give you briefly the use case that I have for wanting to do disaggregation, which is wanting to create like a typical rate class, model to do some forecasting with for utility purposes, but we want to have a gross number, right? We don't want to have the net mixed in there because we're trying to layer on solar as part of our load shape forecasting. So, I mean, obviously one way is just throw out all the solar customers, but there's some bias to that. So if you can instead disaggregate and gross up the net back up to what the, building consumption would be, then you can do the, weather dependent modeling for forecasting purposes. So it's not a pre-post model in the same way, but it's still wanting to like separate weather out so you can use the data for forecasting, and PV is like on you have a totally different part of the model that's forecasting PV because that's responding to a different market condition. But I realize it's not part of this this round, so I'll be patient.
Should I move on to the next slide?
Go for it.
Yeah, we got to get this rolling. We got 2 minutes,
Yeah.
1 minute.
So real quick, okay. Conclusion. Using temperature in most all of the scenarios, temperature was more than enough rather than using all those other weather data set. At least for this population level analysis we had, it was in California. Maybe that's the case. Maybe we need to implement that for other locations. Maybe that's a huge difference, specifically when those places that we have like cloudy areas like Seattle. So those models like extra tree, regular server, random forest tend to overfit on the train set. I could just easily change the depth of the extra tree to 4, and the train error would be complete 0, like vanish all of that. and the test set would be not that bad, like 35% improvement, but you can't rely on these type of methodology. You need to have a balanced model. Solar data, as we mentioned, can reduce the solar customer's error. But as we mentioned, we need to be more careful with that, and we need to have more analysis in terms of, let's see how many cloudy days we have. Do we actually see improvement inside of the load curve and all of those things? So this is actually we see improvement, but we need to be a little bit more cautious about it. And we think PNRMSE can be a better criteria for these type of analysis rather than CVRMSE. That's a suggestion, and we saw that CVRMSE can go negative and can go very high numbers. So that's one thing that we need to consider in the future analysis. And the future work, that rolling window test frame, we want to implement. We pretty much implemented. We're ready for the data set to come to actually train the model on top of that. We need to use larger data set to have more reliable statistics. And again, the GHI model improvement, that's something that we need to do. And definitely we need to want at least one benchmark with the neural nets, with maybe the simple couple layers neural net to see how's the AMR prediction would do. Yeah. Back to you, Travis.
All right. Well, if there are any other questions or somebody's wanting to discuss something, we can stay and talk. Glenn, go right ahead.
First of all, thank you very much for the awesome presentation, and I really enjoyed the discussion, and thanks for everybody's patience on my questions and comments. I was wondering if I could get the model specification, you know, like with all the Greek letters and the summations and things like that, with the subscripts. And also, can you remind me where we're keeping these slides for future reference?
Yeah, the slides themselves are being posted online. And let's see, I can find that web page quickly and just post it in the chat.
Okay, that'd be cool.
You know, I'll actually check too, Glenn, because if we're not posting the slides, we could be and should be. Like, I'd like for us to be posting the slides. There's no reason not to.
Yeah.
But let me send a link on to where there are meeting summaries, and I think, but forgive me if I'm wrong, that we are posting the slides. I'll just find that and send it, post in the chat here in a second.
Yeah, I know at one point in time you were. I remember checking one like 6 or 10 months ago or something, but I forgot where it was, and I wasn't sure if we were still doing that. So,
yeah.
But yeah, but back to the model specification.
So
I know
model
it's the hassle
specification,
to put those Greek letters in there, so just feel free to use the Roman characters or whatever, and parentheses for the eyes and stuff like that. Is that something we have for the 3 final models that we're evaluating there? The 2.0 and the other over the tree regressions or something like that.
for 2.0, I know we have it in the actual CalTrack documents, but for the new models, I'm basically using scikit-learn library, but I can give you a detail about what is the ElasticNet parameters, the inputs are, and then what the most important thing is to introduce your input features, like daily features, goes inside of the model. The model has, I think the best model for the ElasticNet was, the parameters was alpha ratio was 0.1, 0.01, and the other one was like 0.9. I can just like have a summary of the best models that we found, and then attach it to this presentation.
Just a mathematical equation is fine. Yeah.
Okay.
Cool. Thank you very much.
Yeah.
all.
All right. So with that, everyone, we are a little bit over time, and so thank you all for joining us. I hope you learned something. We learned some stuff along the way. So thank you very much, and have a good day.